So, hello to everyone who is watching on YouTube. I guess I'll wait for like 5 or 10 minutes so that a few people can join the session. Few people can join the session in person. So we'll start in I guess like 5-10 minutes. Okay, so it seems that no one has joined the session in person yet, so I guess we can get started nonetheless. So, hello everyone. So just to introduce myself, I'm Lakshya Saggi. I will be the problem solving TA for the Monday 6 to 8 p.m. sessions for the Games and Information course. And like this is our first session, so this is our first problem solving session. So yeah, welcome to the course. So this session will mostly discuss some problems related to the topics which are covered in week one. So this will help you in solving the problems for the week one quiz. And this will be the questions will mostly be based on domination strategies, weekly dominating strategies, and Nash equilibriums. Also, like yeah, I prepared a list of questions, and I hope some of the questions like you'll find interesting. So I guess I'll just share my screen and we can get started with discussing the problems. So I'll just share my screen, guys. Okay, so I hope my screen is visible to everyone. So yeah, I don't have anyone to. Yeah, so I hope my screen is visible, and maybe we can get started with the problems then. Okay, so once again, I'll be assuming that everyone has seen the lectures from the first week of this course because I'll be assuming you guys know what Nash equilibrium is. I'll be assuming you guys know what weakly dominating strategies are and what basically what in general strategies are. So yeah, every all the definitions and all the technical things which were discussed in the lectures, I'll be assuming you know that, and we'll just be focusing on the problems. So let's start with the problems then. So first problem states that, okay, so consider a two-player game whose payoff matrix is given by this. So we are given a two-player game whose payoff matrix is this. So as everyone might know, the standard notation is so basically player one is the row player and player two is usually the column player. So player one has strategies T and B and player two has strategies L, M and R. And we are given this payoff matrix. So, for example, let's say player one plays the strategy B and player two plays the strategy L. Then this is the common intersection of B and L. So, player one will get a payoff of 0 and player two will get a payoff of 3. And yeah, we'll be assuming that both the players want to maximize their payoffs. Like what they get out of the strategy, they want to maximize that. So here, player one will get 0, whereas player two will get 3. So yeah, similarly here, player one will get 1, player two will get 0, and stuff like this. So yeah, but so the problem states that so we have to select the correct options out of the following. This problem just asks about dominating strategies. So the option A is for column player, strategy M dominates strategy R. So for column player, these are the two strategies M and R, and the option is asking whether uh, strategy M dominates the strategy R. So let's just see. So I hope everyone knows what domination is. So domination means that whatever player one plays, uh, we don't care about whatever player one plays, but what player two plays. Like if player two is playing M, then the payoff should always be at least as good as the payoff when player two plays R. This is what domination means on a high level. That is, player two is playing strategy M instead of strategy R, then the payoff for the player two will always be higher, irrespective of whatever player one plays. Something like that. So let's just see here. So these are the payoffs for the second entries are the payoff for the player two. So let's just see. So for player two, if the player two plays the strategy M and player one plays T, then the payoff is 2. Whereas if play like So player one is, let's say, playing T only, and player two, if player two plays like strategy M, then the payoff is 2. Whereas if player two plays strategy R, then the payoff is 1. So here, like, it is beneficial for player two to play strategy M instead of R. And similarly, if player one instead played strategy B, then again we can see that the payoff for player two on playing M is 1, whereas on playing R is 0. So again, we see that 1 is greater than 0. So here also, uh, the strategy of playing the strategy M is better than the strategy R for player two. So so in whatever player one plays, if player one plays T or if player one plays B, it doesn't matter to us. In all cases, what we have is that the strategy M is always better for player two than strategy R because its payoff is higher. So that's why, like, we can say that for column player, strategy M dominates strategy R. So maybe I'll just type the option. Yeah. So I'll just maybe type it out. So this is correct. And why is this correct? Okay, maybe I should just start with some explanations. So if P1 plays P, then payoff for player 2 on playing M is equals to 2, whereas and playing R is equals, or maybe I should just write it like this. So if P1 plays T, then the payoff will be payoff for P2 on playing M is 2, and payoff for P2 on playing R is 1. So here it was 2, whereas it was 1. So we see that here it is better, and case 2 is, maybe I should just write like this. So this was case 1. And case 2 is if P1 plays B. If play 1 plays the strategy B, then payoff, maybe I should just again copy and paste these and change the values. So payoff for P2 on playing M. So what will the payoff for P2 on playing M? So it will be like 1. Whereas on playing R, it will be 0. So in both cases, it can be seen that payoff or payoff on playing M is better, higher than payoff on playing M is higher than payoff on playing R. And hence strategy M dominates strategy R. So yeah. So this is like this option is correct. So let's do the second case also. Like the second let's see for second option also. So it is A option is correct, that for column player M dominates strategy R. Then for second option, we have for row player strategy M dominates strategy R. Okay, so for row player, so row player strategies are T and B, not M and R. So this option is directly incorrect because M and R are not even strategies for row player. Incorrect, as M and R are not the strategies for row player. So C option directly incorrect. Similarly, for column player strategy T dominates strategy B. This is again incorrect because for column player, these are the strategies L, M, and R, not T and B. So again, maybe we should just copy and paste this. So this will be incorrect, as T and B are not the strategies for column player. Then we have the last option which says for row player strategy T dominates strategy B. So for row player, like these are two strategies T and B, and now we are asking whether strategy T dominates strategy B. So maybe if for A part we did it like for case wise, but now for this D option we'll just do it column, like we'll just do it orally now. We don't need to write everything down. So for row player strategy T dominates strategy B, we have to check this. So note that payoffs for row player are denoted by these first entries, right? So now we have to see where whatever, like now what we have to check is whatever column player plays, the row player, if row player is always better of playing T instead of B, then we are kind of done. Then we can say that T strategy dominates strategy B. But we'll have to check this. So let's see if column players, let's see this column, like if column player plays L, then we have to check this column. In this column, we can see that if row player plays T, we get a payoff of 1. Whereas instead on playing B, he gets a payoff of 0. So 1 is greater than 0. So here, like, so at least if column player plays L, then T is a better strategy than B. But now if column player plays M, then again we can see that T is a better strategy than B because again the payoffs are 1 and 0. But if the column player plays R, then the payoff on for row player on playing T is 0, but on playing B is 2. So here you can see that 0 is actually less than 2. So payoff is better on playing B if column player plays R. So what we can say is that strategy T does not dominate strategy B because if column player plays the strategy R, then T is not a better choice over B. B is a better choice over T. So that's why like this is incorrect. And why is this incorrect? Maybe I'll just write the explanation. Because if column player plays R, then row player has higher payoff on playing B over D. Yeah. So only like option A is correct. Like A was correct, B, C, D, both all three are incorrect. So maybe we can just write this down. And only option A is correct. No other options are correct. Note that this there could be multiple possible correct options because we have written like it can be multiple choice. But at least for this question, only option A was correct. Now let's move on to the second question then. So second question is a true or false question. So like since there is no one in the meeting, I would have liked for some people to try to answer this question first before like proceeding to its answer directly. So maybe I'll just discuss the answer directly. So the question says that the order of removal of a weakly dominated strategy. Okay, maybe I should. Yeah. Yeah. Now I think the question is better worded. The order of removal of weakly dominated strategies of each player determines which Nash equilibria are lost. So is this statement true or false? So what this statement says is that okay, you might have seen the lectures that if we remove some weakly dominated strategies from the set of strategies, then whatever Nash equilibria we achieve is also a Nash equilibria for the original game. So now we are asking whether the Nash equilibria which we arrive at for the final game, is it dependent on like the order in which we remove the weakly dominated strategies, or whatever order in which we remove weakly dominated strategies will always be uh, will always arrive at the same Nash equilibria. So actually, like this statement was actually covered in the lectures also. So yeah, like this was just a direct application. This was just a direct like question from the lectures. So actually, this statement is true. Yeah. That actually the order of removal of weakly dominated strategies determines which Nash equilibria are lost. Note that this is because we are removing weakly dominated. But if the problems instead ask for like the order of removal of strongly dominated strategies, then this would not have, then this would statement will be false. Like, because you can always remove strongly dominated strategies in any order. And why is that? This is because if we remove the strongly dominated strategies, no Nash equilibria are lost. But on removing weakly dominated strategies, Nash equilibria are lost. So I hope you get the difference. So maybe I should just say it like, okay, I'm sorry for this. So maybe I should just put a note here. If the problem asks about strongly dominated strategies instead of weakly dominated strategies, then the statement would be false, as no Nash equilibria are lost on removing strongly dominated strategies. Yeah. So this is just a note for the second question. So yeah. Okay. So actually, this statement was true, and when we also complete this, we'll again like we'll have to describe an example. Like if we are claiming that this statement is true, then we have to provide an example, right? Where order of removal of strategies determines which Nash equilibria are lost. And again, I'm just quoting the lecture here. I just quote the example from the lectures. Maybe I'll just copy this table from here. Okay. And like we'll just show a game where order of removal actually determines which strategies are lost. So let's say the values which I put in are not these one something. This is 1 2. This is 2 3. This is 0 3, and this is let's say 3 2. Okay, I'm just reconstructing the example from the lecture. Like I'm just not doing anything new, but just for sake of completeness, I'll try to show you guys again like why is this true. So then this is 2 1. This is 0 0, and this is 1 0. So yeah. So suppose this is the payoff matrix given to us, and now we are claiming that in this matrix, the order of removal of weakly dominated strategies gives us different Nash equilibria. Okay, and in this example, what can we say? So first, let's just identify like if there are like some weakly dominating strategies here. So okay, maybe I should just write this as LCR and this as DMP. Just for like making it in sync with the lectures example. So here, like what you can actually see is so there can be multiple weakly dominated strategies. Like what we say here is let's just see the row players strategy T and strategy M. So you can see if column player plays L, then strategy M is better than L. Then strategy M is better than T. Similarly, if column player plays C, then again M is no worse off than T because both are 2. And if column player plays R, then again M is better off than T. So since like we have equality in one of the cases on playing strategy C, so strategy M is a weakly dominated strategy. Maybe I'll just write that as an example. Discussed in the lectures too. Okay, so here what we can say is so case 1, or maybe yeah, Yeah, case one is M weakly dominates T, right? So we remove T. So if we remove the strategy T from here, let's say, a bit, yeah, now it's better. So we have shown that M is M strategy M weakly dominates strategy T. So what happens here is we can remove the strategy T from this now if we wish to like, yeah, obtain some Nash equilibria. So what we will be left with is the following. So let's say um, we'll be left with the following payoff matrix. Uh, the payoff matrix. So the payoff matrix on removal of T is something like this. So let's say I remove this T altogether. Delete row. So this will be the payoff matrix now for me. And now what we can see is in this kind of strategy, uh, the strategy, let's say the strategies R and strategy L. So strategy R and strategy L will also see that strategy L dominates the weakly dominates strategy R. And why is this the case? Suppose if player one plays M, then L has a payoff of 2 for the second player, and this R also has a payoff of 2 for the second player. But if the row player plays B, then strategy L has a payoff of 1, whereas column player has a payoff of 0. So strategy L is no worse off than strategy R in both the cases if player 1 plays M or B. So again, we can see that strategy M, that strategy L weakly. Okay, maybe I should just write not strategy, but just L. L weakly dominates. Maybe I should just put all of this in the new page. So everything is together. So now L weakly dominates R. So this implies that we can remove R. So payoff matrix on removal of R now will look like. So removal of R, if we remove the R from here, the payoff matrix will look something like this. I just copy and paste the payoff matrix and remove the R from here. Okay, so if I delete the column, now we have two strategies, L and C, and here M and B. And actually, you can now see that this kind of strategy, like this strategy ML here, will be a Nash equilibrium. And why is this the case? This is because suppose I am at the strategy M comma L, then for the column player, if the column player switches to the strategy C, column player will be at a loss. So column player will definitely not switch. Whereas if the row player switches from strategy uh, M to strategy B, then the row player's payoff will remains the same. Like it was 2 here, it will remain 2 here also. So for row player, like there is no incentive to change. Like row player is not strictly better off than before on switching the strategies. So, and this is what essentially we call as equilibria, right? That no player has an incentive, has a positive incentive to switch from the current strategy to another strategy. So for row player, you can see that uh, the row player has no incentive because his payoff remains the same, whereas column player also has no incentive because his payoff actually decreases on switching. So M comma L is a Nash equilibrium. So maybe I'll just color this box. Okay, or maybe we can we can leave the coloring out. So M comma L is a Nash equilibrium, right? And you can actually see that none of the others are Nash equilibria because this B comma C won't be a Nash equilibria uh, since okay, like one thing which you can directly see is the strategy L strictly dominates strategy C. And why is it the case? Because this 2 is greater than this 1. Similarly, this 1 is greater than this 0. So strategy C can also be removed. And between strategies, so strategy L is the only strategy. And between strategy M and strategy B, like the players can pick any of the strategies, like ML and BL are Nash equilibria here. Why? Because even if like BL, suppose we chose the Nash equilibria as B comma L, again the column player has no incentive to switch because column player will have a lower payoff here from 1 to 0. Whereas for the row player on switching, the payoff remains the same. So row player has also has no incentive. So ML and BL are Nash equilibria. So in this example, ML and BL are Nash equilibria here. And now let's say okay, maybe we could have just had a small example, but yeah, maybe just consider this matrix. Maybe just consider this matrix. Okay, guys, sorry for like um maybe like we did not need all of this example. Like this was just in the lectures, but maybe we have a smaller example too. So just consider this matrix, this pair of matrix of uh just 2 cross 2 matrix of four possible like outcomes. Then if so you can actually see here that uh basically uh the strategy M. Okay, maybe okay, like let's just leave it at that. So, okay, okay. So ML and BL here both are Nash equilibria because uh both of these strategies can result in yeah. So both of these have in both of these outcomes, no player has an incentive to change. But now let's say we consider the case two. So this was the case when we removed like when we considered M dominates T and then L dominates R and something like that. But this was our original payoff matrix, right? And now suppose we instead start with removing some other strategies. So case two will be we start removing some other strategies. So here we chose that M weakly dominates T, and we saw that M weakly dominates T, so we chose to remove T. But now if we start with this instead, that let's just look at the strategies B and M, then we can see that again strategy M dominates the strategy B. And why is this the case? Because you can see in strategy M, like row player has, if the column player plays L, then row player has a payoff of 2, here also 2. So no worse, M is no worse off than B. Here you can see that M on playing M we get a payoff of 2, whereas on playing B, row player gets a payoff of 0. So M is strictly better here. And similarly here also M is strictly better than B. So you can see that since there was equality in this case, in if column player plays L, so we can actually say that strategy M weakly dominates strategy B. So now the case is M dominates B. So strategy M weakly dominates strategy B. And now the payoff matrix on removal of B. What will be the payoff matrix if we remove B here? So what we are doing is for finding Nash equilibrium, we identify a weakly dominated strategy and just weakly dominated strategy and just remove it. So now we remove earlier we removed T. Now we'll remove like a M dominates B, so we'll remove B from here. Right. So first I write the whole matrix and then I remove the strategy B. Maybe not like this, but like deleting the row. Yeah. So this is the payoff matrix which we are left with. And now let's compare the strategy C and R for the column player. Okay, so now, so what we are doing is earlier we removed some other weakly dominated strategy. We removed T, but now in the case two, what we are removing is strategy B. And now we'll see that on removing some other strategies, we'll arrive at a different Nash equilibrium. So let's see the strategy C and R for column player. You can see that for the column player, the payoff is given by the second entries. So if the row player plays T, then column player is like the payoff is same on playing C and R. Whereas if row player plays M, the payoff is higher on playing R instead of playing C. Here we get one, here column player gets two. So strategy R weakly dominates T, strategy C. So what this implies is R weakly. So I'm just explaining the example of the lecture again, but maybe like this will help you uh, again understand what was discussed in the lectures. R weakly dominates strategy C. So now we remove. So now we remove the strategy C. So the payoff matrix on removal of C. So what's the payoff matrix on removal of C? So if we remove the strategy C, then we'll be left with the payoff matrix of this kind. Maybe I'll just copy and paste this and we remove the strategy C from here. So delete the column. So we are left with these strategies. So TM and LR. So yeah. And now let's see the possible Nash equilibria here. So here one thing which we can see is so here one thing that we can see is uh like we can like almost directly find out the Nash equilibria here. So one thing which we can directly see here is that the strategy M will be one. So payoff is 1, so 2 is greater than 1, and here payoff is 3, here payoff is 0, so 3 is greater than 0. So for row player strategy, M strictly dominates strategy D. So the Nash equilibria will be one of these two strategies, and from these two strategies, like uh, whatever like we choose, both will be Nash equilibria. And why is this the case? Because if 2 comma 2 was the uh, let's say we are at the condition 2 comma 2, then row player has no incentive to switch because like it can only go to 1 comma 2, so its payoff will reduce if row player switches. So row player does not have any incentive to switch, and similarly column player also does not have any incentive to switch because it just goes from 2 to 2. So again this 2 comma 2 is a Nash equilibria, and like this was again M comma L. So from here we get that one of the Nash equilibria is M comma L, which was the same as before. But if you see this also M comma R, then I claim this will also be a Nash equilibria. And why is this the case? Because again, if we see the row player, then row player, if row player switches, then row player is right now getting a payoff of 3, but on switching it gets a payoff of 0. So row player will not switch. Similarly, uh, for the column player, the payoff is currently 2, but on switching, also the column player's payoff will remain 2. So column player again has no incentive to switch. So ML and M comma R are Nash equilibria. So note that the original payoff matrix was this only, and this can have multiple Nash equilibria. And we saw that if we remove the weakly dominated strategies in this manner, like we remove first T, then remove R, then we obtain the Nash equilibria as these ML and BL. And note that we have discussed in lectures that these will be Nash equilibria of the original payoff matrix also. But if we remove the weakly dominated strategies in this order, that first we remove B, then we remove C, then we obtain this different Nash equilibria, which is M comma R, which we did not get earlier. So what this shows is that if we remove weakly dominated strategies in different orders, we can obtain different Nash equilibria. And that's why this uh, statement is true. That order of removal of weakly dominated strategies determines which Nash equilibria is lost. So I hope everyone is with me till this point. This has also been discussed in the lectures, the same example. I just tried to explain it again. So yeah. Okay, so now maybe we can move on to the third question. So third question says that consider a game involving two players where the set of strategies of player A. Now we'll try to pick up the pace a bit because I think we are now comfortable with the like identifying which are the row players. The row players payoff is the first entry, column players payoff is the second entry, and how do we identify whether it is in Nash equilibrium or not? So consider a game involving two players where the set of strategies of player A is given by A1, A2, A3, A4, and player B is given by B1, B2, B3, B4. The payoff matrix are given by these, and the players are trying to maximize. Obviously, like everyone tries to maximize their payoff. And now we have to choose the right options. So we have to see which of the options are correct. So we have to check if A1 comma B4 is a Nash equilibrium. Okay, so let's just see this option like A1 comma B4. So this is the which option A, and we have to identify whether it is true or not. So note that for identifying an Nash equilibrium, some of you, what you may try is, okay, so identify dominating strategies and remove them. So you can always remove strongly dominating strategies, but note that if you try to remove some weakly dominating strategy, then you might get into trouble because like on removing a weakly dominated strategy, you might be removing one of the Nash equilibria, as we just observed in the previous question. So to find out the all possible Nash equilibria, you should not uh, reduce the problem by removing a weakly dominated strategy. It's okay to remove like strongly dominated strategies, but not weakly. I hope this distinction is clear. So now let's just see here whether this is A1 comma B4 is a Nash equilibrium or not. So first let's see for the column player, whether column player has an incentive to switch or not. So the second entries are the payoff for the column player. So if row players is still at A1, then column player, if the column player plays switches to instead B3, then the payoff is initially 4, but it reduces to 3. So column player has no incentive to switch to B3. Similarly, no incentive to switch to B2 either because here the payoff is 1, here the payoff is 4. And similarly to B1 also because here the payoff is 3, here the payoff is 4. So for column player at least, there is no incentive to switch. But let's see for the row player. So if row player switches to A2, then the payoff is, so first of all, initially the payoff is 5, but switching to A2, the payoff becomes -2, which is again less than 5, so no incentive to switch to A2. On playing A3, the payoff is 4, again no incentive to switch because 5 is greater than 4. And on A4 also no incentive to switch because 5 is greater than 4. So this A1, B4 is actually a Nash equilibrium. So this statement is actually true. So I hope everyone is with me on these explanations. I don't want to write down the full explanation because I think we have already learned how to identify if it is a Nash equilibrium. We just take the corresponding rows and columns and see like if there is an incentive to switch or not. Okay. Then the B part says that A4 comma B4 is a Nash equilibrium. So let's just see if A4 comma B4 is a Nash equilibrium or not. So let's just see from the perspective of the column player first. So for the column player, we can see that the initial payoff is 4. So the column player has no incentive to switch to B3 because here payoff is 2. Here payoff is -2, so again no incentive. But on playing B1, the payoff is 5. So here the column player actually has an incentive because initially the payoff is 4, but here the payoff is 5. So column player has an incentive to switch from A4 to B1, from B4 to B1. So this is actually not a Nash equilibrium. So not where any means Nash equilibrium as column player has an incentive to switch to B1. So what this means is that payoff for column player on playing on basically A4 comma B1 is greater than A4 comma B4. So something like this. Yeah. So that's why B part is not a Nash equilibrium. Now we come to the C part, which is A3 comma B1 is a Nash equilibrium. Let's just see if A3 comma B1 is a Nash equilibrium. So A3, also note that it is always not necessary that determinist. Okay, maybe we'll come to that later. Yeah. So A3 comma B1 is a Nash equilibrium. So the statement is claiming that A3 comma B1 is a Nash equilibrium. So let's just check here if it is, indeed is a Nash equilibrium. So let's just check for the row player first, whether row player has an incentive to switch or not. So the row player's payoff here is 8. And we'll see that, okay, if row player switches to A4, then the payoff becomes 1. So no incentive to switch here as 8 is greater than 1. Similarly, no incentive to switch to A2 either because 8 is greater than 0. Similarly, 8 is greater than 5. So row player has no incentive to switch from A3 to any other. But let's see for the column player. For column player right now, the payoff is 4. And on switching to B2, the payoff becomes 0. So no incentive to switch to B2. No incentive to switch to B3 either because it is -2. And similarly to B4, also no incentive because it's again 2. So 4 is greater than 2. So we see that actually A3, so neither row player nor column player has an incentive to switch. And that's why this A3, B1 is also an Nash equilibrium. So yeah. So like none of these is not definitely not correct because we have identified that two of the statements are true actually. So yeah. So hence maybe I should just write down the answer. Hence options A and C are correct. Yeah. So yeah, we just had tried to identify Nash equilibria. So the purpose of this problem sheet is mostly for you guys to identify what is a Nash equilibria and what is not. And like there are some good questions at the end of this sheet also. So yeah, we'll be discussing those two. Okay then. So let's come to the fourth question. So fourth question says that consider two nodes, one named source and the other named terminal, and they are interconnected via root A and root B. The cost, so there are two roads. So there is a source and there is a terminal, and there are two routes. One is A and one is B. The cost of traveling from S to T using the route A is given by fraction of agents using A, and that for using B is always 1. Suppose there are a total of n agents traveling from S to T, and Na denotes the number of agents using A, then the cost of traveling via route A is given by Na by n. So actually what the problem is stating is that basically there are two routes for going from S to T, and one route always has a length of 1. This route B always has a length of 1. And the route A actually has a cost which is equal to the number of agents using that route. So let's say so the cost is given by if Na is the number of agents using the route A, then the cost of traveling for every agent is Na by n. So what this means is that suppose there are total 3 agents and only one agent goes through route A and both other agents go through route B, then since only one agent is traveling, so the cost for traveling through route A will be 1 by 3. So this is the kind of question. So basically the cost of traveling through the route A is different for different strategy profiles. So now the problem statement says that for n equals to 3, if we formulate this problem as a game where each player's strategy is the choice of the route, it takes to travel from S to T, and each problem wants to minimize the cost of travel, then choose the right option. Okay. So what this means is that let's say we have three players, and all the three like and all the three players have two choices, right? Whether they want to go through A or whether they want to go through B. And now we can think of this as a Nash equilibrium game where each player wants to minimize the cost of travel. But if all so basically if all of the agents try to go through B, then there is always incentive for at least one agent to switch to go through A because A is currently empty. So if one agent goes through A, then the cost of using A will be 1/3 only. So something like that on it. So I'm not going to write down the proper maths for this, but maybe we can just discuss it only. So we have to choose the right options. So there is no Nash equilibria for this game. Okay, maybe we'll try to come to this option later because right now we don't know if there is or if there is not. Okay, so let's see the problem. Let's see the option B. So the option B says the strategy profile AAA is a Nash equilibrium. So what does strategy profile AAA mean? It means that all the agents, all three agents, so there are three agents given to us. So all three agents take the route A. Okay, so what happens is uh, if all three agents take the route A, then cost of traveling through A is equals to 3 upon 3, which is equals to 1. Right? Maybe I should write this as like this. And cost of traveling through B is also equal to 1. So you can see that note that cost of traveling through B is also 1. So no individual agent has an incentive to switch to B. So let's say, let's consider any of the agents. Let's just consider the first agent. If the first agent's current payoff is 1, not payoff, but let's say the cost, and the agent wants to minimize the cost. So right now the agent's cost is 1, and agent wants to minimize it as much as possible. So if the first agent tries to switch to the route B, then again the cost for this agent still remains 1 because right now it's 1, and on switching to B also it will be 1. So the agent has no incentive to switch. So basically the first agent will not switch. Similarly, second and third agent will also not switch. Hence, no agent has an incentive to switch to B. Hence, AAA is a Nash equilibrium. Sorry. So note that NE means Nash equilibrium. So at least we have obtained one Nash equilibrium. So we are certain that this is definitely incorrect. That there are no Nash equilibria. The option A is definitely incorrect because there are no Nash equilibria. This is incorrect because we have obtained. Okay, sorry for this, guys. I don't know what happened here. So yeah. So A is a Nash equilibria. So at least we know that there exists some Nash equilibria. Now let's go to option C. So option C says that strategy profiles AAB, ABA, AAB, and AAA are Nash equilibria. So we know that AAA is a Nash equilibria. And let's just see for these kinds of options. So what these options means is that effectively two players choose the path A and one player chooses the path B. So if two agents are taking the path A, if two agents take the route A, then the cost of traveling through A is equals to 2 out of 3, right? And the cost of traveling through B is actually 1. So, so no agent which are taking this route A will have an incentive to switch, because whatever agent is taking the route A has a cost of 2 by 3. If the agent switches to B, it will have a cost of 1. So none of these two agents who are taking the route A will have an incentive to switch. But what about the agent who's taking the route B? So if some agent is taking the route B, if exactly one agent is taking the route B, then what happens is, if suppose if that agent decides to switch and decides to take the route A instead. So initially the cost for that agent was something like a 1. But if the agent decides to switch to A, then what happens is, now instead of two agents taking the route A, the third agent is also taking the route A. So the cost of traveling for all agent now becomes 3 by 3, which is equal to 1. So the agent which decided to switch from route B to route A will again have a cost of 1 only. So initially it had a cost of 1 by traveling through route B, and on switching to A also it has a cost of 1. So again, the agent traveling through B will not have any incentive to switch, and this will be an Nash equilibrium. So this is the high level idea. Maybe I'll just write it down also. So agents traveling through A have no incentive to switch as 2 by 3 is less than 1. Also, the agent traveling through B also not have an incentive to switch, as its cost on switching to A is equal to 3 by 3, which is equals to 1. So again, it has equal cost. So 1 equals to 1. So again, the agent has no incentive to switch. Okay, I see. So that someone has joined the meeting. So hello, Prashant Shakya. So if you just joined the meeting right now, so like we are 1 hour into the meeting, but maybe I'll just try to give you a recap of what we have been doing. So so this is our first problem solving session, and this week we are just discussing the problems related to Nash equilibria and strongly dominating strategies and everything. So some we have discussed some of the problems on based on two-player games where we had to find like strongly dominating strategies in payoff matrices, and similarly some Nash equilibria and stuff like that. So there's a bunch of problems which I had created for us to solve in practice. So yeah, so we are right now at the fourth problem. And the fourth problem, maybe since we are solving it right now, I'll just explain it to you again. So in the fourth problem, we have that we have two nodes S and T, and which are connected via route A and route B. So there are two roads connecting source and sink, source and terminal, and cost of traveling from S to T using the route A. So there are two routes. For one route, the cost is actually dynamic. It is given by the fraction of agents using A. And for B, and if we use the path B, then the cost is always 1. Suppose like there are total 3 people, and someone decides to, like, two of the people decide to take the route A and third the person decides to take the route B. So those two people will only have to pay like 2 by 3 cost, because cost of traveling via route A is given by the number of people traveling through A divided by the total number of people. So if two people are traveling through A and there are three number of people overall, then the cost of traveling through A will be something like 2 by 3. So like this is kind of the problem that And we have to figure out like the Nash equilibria for this kind of a game. So first we saw that the strategy profile A will be a Nash equilibrium. And why is this the case? Because of all three agents take the route A, then the cost of traveling through A becomes like 3 by 3, which is equal to 1. So each of these agents, so all agents first of all want to minimize their cost. And right now, if all three agents take the route A, then all of these are paying 1, 1, and 1. And so if any of the agent decides to switch, they'll anyways have to pay a cost of 1 because cost of using B is always equal to 1. So none of these agents will want to switch from here. So this is a Nash equilibria. And similarly, now we are at the C part where we say that suppose like so we know that AAA is a Nash equilibria, and now we have to see whether AAB, ABA, and AAB are okay. Maybe this is B. This should be BAA. Whether these three are Nash equilibria. Yeah. Uh, yeah. Sorry for that, guys. Yeah. So we have to see whether if two agents decide to take the route A and third agent decide to take the route B, whether this is a Nash equilibrium or not. And this was what I was discussing. If two agents take the route A, then the cost of traveling through A is actually equal to 2 by 3. So the agents which are traveling through A will have no incentive to switch because they are currently paying a cost of 2 by 3. And if they switch, then they have to switch to B, which has a cost of 1. So no agent will want to switch to B as 2 by 3 is less than 1. And now the agent traveling through B, suppose there is an agent which is traveling through B. The third agent is traveling through B. That agent is already paying a cost equal to 1. And now if that agent decides to switch to A, what happens is note that the cost for taking the route A no longer remains 2 by 3. Because now if the third agent also switches to A, then what happens is all three agents are taking the route A. So the cost of taking A if the third agent also decides to switch will be equal to 3 by 3, which is 1. So the third agent who is right now taking the route B will have no incentive to switch, as if it switches, the cost of going through A increases and becomes equal to 1. So since 1 equals to 1, the agent will not have any incentive to switch. Okay, I think we can move on to the B part now. Okay, yeah. The strategy profiles ABB, BBA, and BAB. So we know that AAA is a Nash equilibria, but whether these three are also Nash equilibria or not. So these three strategy profiles basically correspond to if exactly one agent is taking the route A. If one agent takes the route A, then we know that the cost of traveling through A will be the fraction. Then the cost of traveling through A is actually equal to the fraction of agents taking the route A. So it will be 1 divided by total number of people, which is 3. This will be equal to 1 divided by 3. So again, note that the agent which is traveling through A will have no incentive to switch because if it switches to B, then it has to pay a cost of 1. Right now it's paying a cost of 1 by 3. So this agent has no incentive to switch. So the agent traveling through A has no incentive to switch as 1 by 3 is less than 1. Maybe I should just keep fractions together for it to be a bit more legible. Yeah. So 1 by 3 is less than 1. So that's why this agent has no incentive to switch. But let's see for the other two agents. So consider an agent which is traveling through B right now. Now, if that agent decides to switch to A, what happens is that agent is, if traveling through B, is paying a cost of 1. But if that agent decides to switch to A, then exactly, so there's this one agent which is traveling through A. And now if another agent decides to switch to A, which was currently traveling through B, then two agents will be traveling through A and one through B. So then these two agents traveling through A will have to pay a cost of 2 by 3 now. So the agent which decides to switch from B to A was initially paying a cost of 2, cost of 1, but now on switching has to pay a cost of 2 by 3 because the fraction is equal to 2 by 3 now, the people traveling through A. And since 2 by 3 is less than 1, that agent will indeed want to switch. So yeah, so maybe I should. But an agent traveling through B will have an incentive to switch as its cost on switching to A is equal to 2 by 3 because now two people are traveling through A, one which was already traveling and the second this one. So now, and this 2 by 3 is less than 1. So yeah, that's why this person will have an incentive to switch. Hence, uh, this is not a Nash equilibrium because some agent has an incentive to switch. So maybe I should just underline these. So this is a Nash equilibrium. So this is a Nash equilibrium. And this is not a Nash equilibrium. Yeah. So we see that option B is correct and option C is correct. So option B and C are correct. Like there are no Nash equilibria. This is wrong because we have already obtained Nash equilibria. So option B and C are correct and option D is incorrect. So options B and C are correct. Hence options B, comma C are correct. So I hope this is clear to everyone. Then again, we come to some of the games. Yeah. And this will be of a different flavor. Here we are not asking about the Nash equilibrium for this problem, but what we want to arrive it as is the like, can we arrive to the final like Nash equilibrium by strictly identifying strictly dominating strategies? So the fifth problem says that we are given a two-player game, like with this guy, and we have to calculate the final payoff by iterated elimination of strictly dominated strategies. So we don't have to find out the Nash equilibria right away. Like it's not like we have to find a Nash equilibria by just identifying any pair where there is no incentive to switch. But we have to do this by elimination of strictly dominant strategies. And we know that like we can remove the strictly dominant strategies in any order. It does not affect the Nash equilibria at all. So if we arrive at a single pair of strategy by strictly dominated strategies, then we are good and we have to mention the strategy. Otherwise, we have to say that we cannot reduce this using just strictly dominated strategies. Yeah. So this kind of problem is there in a quiz. So that's why I think this kind of problem is important. So let's see here. So let's see if there is a strictly dominated strategy present in this payoff matrix or not. So just let's consider first let's compare these two strategies, L and R for the column player. So we see that for column player, like if row player plays T, then for column player, like R is a better choice than L. But if row player plays B, then L is a better choice than R as 3 is greater than 1. So between R and L, we can't say that one is strictly dominating the other. But now let's compare the strategies T and B now. So for strategy T, let's see. Uh, so in strategy T for player 1, if the column player is playing the strategy L, then this player gets, the player 1 gets a payoff of 1. Whereas on playing B, it gets a payoff of 0. So T is better than B if column player plays L. Similarly, T is better than B on if column player plays R also, because here also the payoff is 1 on playing T, whereas payoff is 0 on playing B. So there is no equality here. 1 is greater than 0, 1 is greater than 0. So this is actually a strictly dominating strategy. So what we arrive at is so T strictly dominates B, and the payoff matrix on removing B is, so then we remove B, and what this gives us, sorry for this guy, yeah. So what's the payoff matrix on removing B? It's something like this. Let's just copy this and just retrieve this. Yeah. And now we have to see if one strategy strictly dominates the other. So role player only has one strategy, so we have to see in this payoff matrix whether strategy L. So note that initially strategy between strategy L and R, there was no one strategy which was dominating another. But it may be the case that in the reduced matrix, in the reduced payoff matrix, a strategy now starts dominating the other strategy. And this is what we mean by the iterated elimination of strictly dominated strategies. So this is very important, guys, that it may be possible that between two strategies, one strategy may not strictly dominate the other initially, but after eliminating some strategies, it actually starts to dominate, as will be the case here. As you can see that there is strategy L and strategy R, and there is only one strategy for the row player. So you can see that the payoff for column player on playing L is 0 and on playing R is 2. And since 2 is greater than 0, so and that's why dominates L on, so on removing B. Yeah, so I think there's some issue going on. Yeah. So on removing L, so on removing strategy L, what we get is that final strategy pair as T comma R. Because we remove this L, then only this T comma R remains, whose payoff is equals to 1 comma 2. So player 1 will get 1 and player 2 will get 2. So this is the final payoff for us. Yeah. In this example. And note that so initially L and R, between L and R, no strategy strictly dominated each other. But after one elimination of a row, R started strictly dominating. And now we iteratively eliminate. And we have to see like, yeah. So it may be possible that still also L between L and R, it could have been possible that there was no one strategy strictly dominating the other. And in that case, we would have said that the process does not reduce to a single player strategy, single pair of strategy. In sixth question, the case. So sixth question is again a similar question. So sixth question says that maybe I should put it in the next page. Yeah. So again, we are given a consider two-player game, and now this is a 3x3 payoff matrix. And now we have to again calculate the final payoff by iterated elimination of strictly dominated strategies. So again, we have to see if one strategy strictly dominates the other. Okay, so let's start with this guy. So let's compare between, like, let's say the strategies L and M. I don't know if there will be any strategies which strictly dominate. Let's just try out all the strategies. So between L and M, we see that these are for strategies for the column players. So we'll look at the second values of the matrices. So we know that on playing, if the row player plays T, then 1 is greater than 0. So L is the better choice, strictly better choice. On if row player plays C, then again 3 is greater than 0. So L is a better choice. But here we see that 2 is actually less than 5. So if row player plays B, then L is not a better choice, but M is a better choice. So between L and M, no strategy dominates any other, because there are cases where some cases where L is strictly better and some cases where M is strictly better. So now let's compare between maybe M and R. I don't know. So between M and R, let's see. So In the first row, we see that 0 is less than 2, so R is strictly better. In second row, also 0 is less than 2, so R is strictly better. But in third row, we see that 5 is greater than 1. So M is a better strategy than R here. So again, between M and R, we cannot say that one strategy strictly dominates other because in some cases M is better, in some cases R is better. Now let's compare maybe the third pair also. Like I'm just comparing the strategies between columns right now. So between L and R, let's see which strategy, if there is a strategy which strictly dominates the other. So we see that here 1 is less than 2, so R is better. But here now we obtain that 3 is greater than 2. So in this row, like L is better strategy. So again, in between L and R, there is no strictly dominating strategy. So in between the column strategies, we have tried all the three choose two pairs. There is no strictly dominating strategies in the columns. Let's see if there is one in the rows. So let's compare these two strategies, the T and C. So here we see that the row play. So now we are looking at strategies for row player. So for row player, we'll be seeing the first values of all the first entries of the matrices, the matrix cells. So we'll be looking at the first values. So between T and C, we see that if the column player plays L, then the payoff on playing T is 1 and on playing C is 1. So note that there's an inequality here. So we can directly deduce that there is no strictly dominating strategy between T and C because like since there is an equality at best, there can be a weakly dominating strategy, but not a strictly dominating strategy. So between T and C, there is not a strictly dominating strategy. Now let's compare between C and B. So in the first column, we see that B is a better choice because 1 is less than 2. But in the second column, we see that 1 is so both have a payoff of 1 for the row player. And so again, it can at best be a weakly dominating strategy and not a strongly dominating strategy. So between B and C also, there is no single strongly dominating strategy. So now let's look at the last possible pair. So we have identified we have tried all the possible column pairs of strategies. We have tried these TC and CB pair of strategies. Now let's see between B, T, like between these two strategies, B and T, which is better if there is a strictly dominating strategy. So we see that in the first column, 1 is less than 2, so B is strictly better. But in the second column, we see that 2 is greater than 1. So here, actually, T is better than B. So again, we have an instance where B is better and another instance where T is better. So here also there is no strictly dominating strategy between T and B. So we have tried all pairs of rows and we have tried all pairs of columns and we have not found a strictly dominating strategy. So one takeaway from this problem is that strictly dominating strategies need not always exist. So uh, we see that no strategy strictly dominates the other. Yeah, no strategy strictly dominates the other. So this is the correct answer. Yeah, yeah. So yeah, there is no single strategy which strictly dominates the other. And get it. Can we move this out of this with this page? Sorry for this, guys. Okay then. Okay, so now let's look at the seventh problem. And seventh problem is consider the game of, okay, so maybe this is something you will relate to a bit more from the real life. So if we consider a game of rock, paper, scissors, so I hope everyone has played the game of rock, paper, scissors when they were um, when they in their childhood. So in rock, paper, scissors, the notion of the game is quite clear that there are two players and both can choose between rock, paper, and scissors, and paper beats rock, scissor beats paper, and rock beats scissors. So basically, there is no strictly better choice to make between rock, paper, and scissors. It's there is no single out of three which defeats the other two. So yeah, so this is kind of the high level idea of rock paper scissors, and this is what the payoff matrix for rock paper scissors also look like. So if player one chooses rock, player two chooses rock, then it's a tie, so both get a zero. If player one chooses paper, player two chooses rock, then paper beats rock, so player one gets a one and player two gets a -1. Similarly, if player one chooses scissors and player two chooses rock, then it's actually a -1 because player one loses and player two wins, so -1, 1. And note that all these entries are filled using this manner only. And now the problem asks us to find the deterministic Nash equilibrium if it exists. And what do I mean by deterministic Nash equilibrium? So what I mean is like, okay, maybe you'll appreciate it a bit more, the word deterministic, in the coming lectures. But what I mean is that, is there a single pair of strategies which is a Nash equilibrium? So so these are these nine strategies like rock, 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 these are these nine strategy profiles like rock, 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 paper, rock, scissors, paper, rock, paper, 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 scissors, and these three also. So out of these nine strategy profiles, does there exist a strategy profile which is also a Nash equilibrium? That is, in that strategy profile, no player has an incentive to uh, switch. So let's just see here. So let's suppose consider this scenario where the player one chooses rock, player two also chooses rock, and note that it will be like a kind of symmetrical, like okay, that if player one chooses paper and player two chooses rock, it will be similar to like player one choosing paper, player one choosing rock and player two choosing paper. So these will be kind of similar, just with signs reversed. But nevertheless, so let's see this. If both players choose rock, let's see this strategy profile. So is this a deterministic Nash equilibrium? So let's see. So if both players choose rock, rock, then let's see if any player has an incentive to switch. And we see that the row player directly has an incentive to switch, because if column player has chosen a rock, row player will want to defeat the column player by switching from rock to paper. As can be seen here, that row player has a payoff of 1 on switching to paper. So paper will beat rock then. 1 is greater than 0. So this is not a Nash equilibrium. Similarly, if we go here and we see that, and we see if this is a Nash equilibrium or not. So if we have a paper, so if we have this 1 comma -1, that player 1 takes out paper and player 2 takes out rock, then does any player have an incentive to switch? So note that row player already does not have an incentive to switch because it's already winning, like paper is beating rock. On switching, like it can only go from 1 to -1 or 0. So row player does not switch. But column player has an incentive to switch here because like column player will want to like get better than this -1, right? So column player can switch to paper or scissors. And in both of these cases, its payoff will be higher than this -1. Here the payoff is -1 for column player. On switching to paper, it will be 0. On switching to scissors, it will be 1. So again, like column player does not has an incentive to switch here. Similarly, in scissors, rock also you will see that there is an incentive to switch for the row player. And like we can see for actually all the values, there will be an incentive for a player. There will be an incentive for a player to switch to another value. So, so actually, no deterministic. Stick Nash equilibrium exists. Okay, so I hope it is clear. And note that yeah. So this problem was mainly to get you guys familiar with that. It's not necessary that you'll always get a strategy profile at which no one wants to switch. So we have this definition of a Nash equilibrium, like in deterministic sense that like it's a deterministic Nash equilibrium if there exists a strategy profile from which no one has an incentive to switch, but it need not always exist. So yeah. So this is an example which shows that it need not always exist. But yeah. So one cool thing to note here though is that like you will see it in the upcoming lectures that but there is some notion of a Nash equilibrium which always exists. Like I'm not saying that this deterministic Nash equilibrium, but still like there is some notion of Nash equilibrium which kind of exists, which is called a mixed Nash equilibrium, which you will like see in the upcoming lectures, I hope. Yeah. But anyways, maybe we can go to the eighth question. So maybe we should. This question is a bit long. So there are last two questions left for the day, eighth and nine, and these are a bit more challenging questions, and I hope you guys will appreciate these questions. So previous questions were a bit more like for to help you in quizzes and a bit more routine questions, but these are last two questions are a bit challenging questions and will make you understand the concepts a bit more. So your question says that, so again, similar to the root A, root B kind of question, but with a different flavor. And I'll try to tell you guys like why is this so important. So there is a suburb S and a train station T and a fixed number of drivers who wish to commute from S to T. For the moment, assume two non-interfering routes from S to T, each comprising one long wide road with travel time 1 hour, no matter how much traffic uses it, and one short narrow road with travel time in hours equal to the fraction of traffic using it. So, like similar to the previous question, that the previous question where route A had the cost equal to the fraction of people going through route A, and route B had a fixed cost of 1. So here also, like the kind of initial network is something like this. Like this is the initial network. Like this is the diagram for the A part, that from S to we wish to travel from S to T, and the routes are like this, that both the routes consist of these two roads where cost of one road is equal to 1. Here like VT road has a cost equal to 1, and similarly SW road has a cost equal to 1. But this SV road and this WT road has a cost equal to the fraction of people using it. So we can think of it as a cost, or we can think of it as the amount of time it takes to travel through this road. Like if anyone travels through this road, it takes 1 hour. If anyone travels through this road, it takes like X hours, where X can be a fraction, like 0.5 hours, which means like something like 90 minutes or something. So these are the roads given to us. So for now, like let's just forget this B part. This will come later. But let's just consider this A part. So in A part, you can see that, okay, so the combined travel time on one of the routes. So you can either take this route, so you can go from S to V to T, or you can take S to W to T. Note that this is the directed graph, so you can't go like S to W to S to W to V or something like this. So there are only essentially two ways for you to go, from S to V to T or S to W to T. And so the total travel time over both of these paths will be something like 1 plus X for any person, right? Because this is X, this is 1, so it will be 1 plus X. But note that the fraction of people using this road might not be equal to the fraction of people using this road. So SV might be equal to X, and WT, like cost of WT, will be equal to some Y, right? So the cost of this path will be 1 plus Y, and this will be 1 plus X. And now the problem asks us, in a Nash equilibrium in A part, how will the traffic spread between the two routes? So like how much fraction of traffic will go from the above route and how much traffic will go from the lower route in a Nash equilibrium? This is what we want to find out. Okay. So maybe how do we see this? Like how can we think of this as a game? Maybe just we can think of these as strategy profiles that like consider the strategy profile x1 comma x2. Okay, maybe like let x1 comma x2 denote the strategy profile where x1 fraction go through SWT and x2 fraction go through. Okay, so first is SVT and the second is SW3. The SWT go through SWT. And since there are like so this is so a strategy profile so this x1 and x2 will like go through from 0 to 1s because these are fractions of people going from like fraction of people. So all people will be going from S to T, right? So we know that some people will go through SVT, others will go through XWT, and these will not overlap. So first observation is that note that x1 plus x2 is equals to 1 because like this is because like the sum of fractions should be equal to 1. And yeah, so one valid strategy profile is maybe 1 comma 0, other valid profile is 0 comma 1, 0.5 0.5 is also valid, 0.7 0.3 is also valid, and so on. And now we want to see which of these. So these strategy profiles will be spread over something like real number space, like and now we want to see that at uh, which of the for what values of x1 x2 will we have a Nash equilibrium. This is what the question essentially asks, like how will the traffic split in the two routes, which just means we need to determine like x1 and x2, right? And that will be the corresponding strategy profile. So note that first of all we saw that x1 plus x2 is equal to 1, and now let us say like so let's think if x1 is greater than x2. So if x1, suppose we are in the, suppose it is the case. So there can be three cases, right? There can be three cases. There are three cases, and what are the three cases? Uh, case one is okay. Yeah. So case one is maybe x1 is greater than x2. In this case, yeah, case one is I should be using bullets like this. Yeah, much better. Yeah, case one, x1 is greater than x2, and in this case, suppose like x1 is actually greater than x2, the fraction x1 is greater than x2. What it means is that more people are going from above than there are people going from below, right? So, so the cost of taking SVT is equals to 1 plus x1. Okay, maybe I can write here also. Then the cost of taking SVT root SVT is equals to 1 plus x1, and cost of root SWT is 1 plus x2. Yeah. So if the so suppose x1 is greater than x2 now, that the so what this means is that 1 plus x1 will be greater than 1 plus x2. So what this means is that the people taking the above route, the SVT route, will be paying a higher cost than the people taking the lower route, right? Also, we assume that these fractions are like, so these x1, x2s are continuous, that there are a very large number of people, so that like even a fraction like 1 by 99999 is realizable or something like that. That these x1, x2s can change by very small epsilons also. Like we'll be needing this kind of thing. So so if x1 is greater than x2, what this means is that 1 plus x1 will be greater than 1 plus x2. So what this means is that the people in the above path are having a higher cost than people in the lower part. So what this means is that there will exist some very small number of people. Like if very small so let's just consider any one person who is in the traffic, right? If that person decides to switch from this part to this part, then that person will be paying almost like 1 plus x2 cost only, because let's say the number of people are very large, that like if something changes by 1 by n, where n is very large, it does not matter. Or maybe like a better way to frame this would be, suppose some epsilon people, like so this fraction is x1, the people taking the upper part is x1, right? Suppose let's just be, if the fraction, if this fraction reduces by some very small epsilon, where like epsilon is very very small, then the cost of taking the upper part would become like something like 1 plus x1 minus epsilon, whereas the cost of taking the lower part will be 1 plus x2 plus epsilon, right? So what this means is that but if we choose a small enough epsilon, then 1 plus x2 plus epsilon is smaller than the original 1 plus x1. And what this results in is that some people will want to try, people will want to prefer like SW, people will want to switch from the current SVT path to the SWT path. So maybe I should like formalize this a bit. Then we claim that people taking the path SVT will have an incentive to switch to SWT. And this will be because devise this, like maybe I should not put it like too mathematically as it will take away the intuition. But what this means is that I suppose this is 1 plus x2, this is 1 plus x1, and x1 is greater than x2. So what this means is that I can reduce this x1 by a very small amount, like very, very small fraction of people choose the SWT path now instead of SVT path. So very small number of people now go to this SW through this SWT part. And now what happens is that for those people, like let's say the small amount is equal to epsilon. For those people, the new cost will be equal to 1 plus x2 plus epsilon, whereas it was previously equal to 1 plus x1. So if they took this path, it was equal to 1 plus x1, but now they are taking this part, so it will be 1 plus x2 plus the new like epsilon which is added because they have transferred. But note that this epsilon can be very small, and hence 1 plus x2 plus epsilon will be can be smaller than 1 plus x1 still. So so 1 plus x1 will anyways be greater than 1 plus x2 plus epsilon, as this epsilon tends to 0 and x1 is greater than x2. So that's why uh, this taking this part will have a smaller cost than taking this part for the people who decide to switch. So there will be people who will have an incentive to switch. And so, yeah, this is not a not a Nash equilibria. So in this case, there will be no Nash equilibria. Yeah. And similarly, in case two, let's say in case two, we assume that x1 is less than x2. Here, people will have a preference to take the SVT path. So if this is smaller than this, then the people from SWT path will instead prefer to take the SVT path. And that's why no Nash equilibria will be present in this case also. And lastly, we come to the case 3, which is like if x1 is not equal, greater than x2 or not smaller than x2, then it will be equal to x2. And so what this means is that if x1 is equal to x2, uh, what happens is if x1 is equal to x2, then we know that x1 plus x2 is 1, right? So if x1 is equal to x2, then it both are equal to 0.5. 0.5 is equal to x2. And now if both are 0.5, 0.5, both are equal, then even if you take very small epsilon amount from, if someone decides to switch from like SVT to SWT, then the cost will actually increase. Right now, the cost for both of these is 1.5, 1.5. But if someone decides to switch from here to here, then the cost will increase from 1.5 to 1.5 plus epsilon, which nobody wants. So no one will have an incentive to switch. No one has an incentive to switch. Maybe we'll, yeah. So hence, this is a Nash equilibrium. So yeah. So although we know that there can be multiple Nash equilibria in many games, like we saw previously in payoff matrices, but in this specific problem, in this A part, we only have one Nash equilibria because x1 is greater than x1, x1 is less than x2 is not possible, and only x1 is equal to x2 is possible. So yeah, hence the yeah, what's happening here? 1 second. Hence Nash equilibria here is equal to 0.5 comma 0.5. And what this means is that is the traffic splits evenly, right? Okay, so this is good. So what this means is that the traffic has split evenly, and so like this is 0.5, 0.5. So the cost for reaching from S to T will now be something like 1.5 for everyone. Now suppose what we do here is we do something very interesting. Yeah. What we do is now in the B part, we install a teleportation device allowing drivers to travel instantly from V to W. So what we do is, okay, we see that there is some traffic on the road that this path will take 1.5 and like 1.5 hours, like this path will take. So everyone is taking 90 minutes in this case. 1.5 hours is equal to 90 minutes. But suppose what the government decides, okay, maybe this is a bit too much, 90 minutes is a bit too much. So let's just help the people here and like add an additional edge which takes you very fast from VW. So what this edge does is it takes you in zero time from V to W. So basically you can teleport from V to W independent of the road condition. So now we have to find out how will the drivers react to this? Like what will be the Nash equilibria in this kind of case? Maybe I'll not write down the everything, but we'll discuss this orally. So what we are trying to do is, okay, so we saw that here everyone's taking 90 minutes. So maybe to help everyone to reach the destination faster, what we instead decide is, okay, we leave these roads as it is, but we install an additional road now. And this additional road is much faster. Like it instantly teleports you from V to W. And now what we do is we see what happens to Nash equilibria in this kind of case. So again, if we see the strategy profile, like people who are taking something like, let's say, some people will take this SV route and some people will take this SW route, right? So let's say some people, so let's say the fraction of people taking this SV route here is x1 and people taking this SW is x2. So note that uh, what happens is, yeah, so the people taking this SW route will have a cost of, they'll go from SW to WT. So they will have a cost of 1 plus x2. Here the cost will be 1 plus x2. And here what we see is that as soon as people go from S to V, like this cost will be x1. And now they will be presented with two choices, that either they take this route of length 1 or they take this instant route and then go to this part. And this will have a cost of something like, yeah, this will have cost equal to the congestion. But note that congestion is always less than equal to 1, right? So like what I'm trying to claim is that uh, so what I'm trying to claim here is so there will be a Nash equilibria here, which will look something like I think this kind of Nash equilibria will be there. That this is one and yeah, 0.5, 0.5. Yeah, 1 second, guys. So this will be yeah. So let's just see like so what I'm trying to say here is let's just see like if we remove some weakly dominated strategy and try to arrive at some Nash equilibria, what will happen? So let's just say if some people who are going from S to W, then W to T, they'll have a cost to pay or something like 1 plus x2 if only x2 people are going here. But what actually happens is it is not 1 plus x2, but what happens is like some people go from S to V and now they are presented with a choice. Like let's say x1 fraction goes from 1 to S to V. So this is equal, like the cost they pay is equal to x1. Now from V to T, they have a choice either to go to W and then to T or just go to T directly. So note that going to T directly will always have a cost of 1. Whereas for going from V to W and then W to T will have a cost equal to like this cost will be 0 V to W and then this W to T cost will be equal to the fraction of uh, vehicles going through WT path. And note that a fraction is always less than equal to 1, right? So what we can say is that if people choose going to this V to W to T, then there is no incentive for them to switch to this path, V to T path. If someone has a ride at V and it goes from V to W to T, then it does not have any incentive to go through this V to T path instead. So what we can actually assume is that like what we can think is one of the Nash equilibria will be in the case when like this T path is never taken. So what we are doing is everyone goes from S to V, then V to W to T, or everyone goes from S to W to T directly. And what this causes is something very interesting. So let's just see what happens here. So basically what happens is if everyone so basically everyone going out from S meets at W, because some people go out from S to V and some people go directly to S to W. But now what happens is everyone who goes to V come back to W. So now the fraction of people coming to W is equal to 1, like because everyone is taking this path now. This W to T path is everyone is taking because everyone is going from S to V to W to T or directly from S to W to T. So now the cost for this W to T will actually be equal to 1 now. So since everyone is taking this path, the cost will be actually equal to 1. And here what's going to happen is again uh people like so what I'm claiming is what everyone will be doing is no one will have an incentive to switch if everyone goes through this path. If everyone takes the path from S to V to W to T, then no one will have an incentive to switch. As we saw that no one will have an incentive to switch to go through V to T, first of all, instead of V to W to T. And also no one will have an incentive to switch to directly go from S to W to T. And why is this the case? Because like if someone goes from S to W to T directly, then they are paying in the path S to W a cost equal to 1. Whereas if they go from S to V to W to T, in the SVW path, they're paying a cost equal to x plus 0, which is equal to x. And this will be a fraction. And so this is no worse off than 1. So no one will have an incentive to switch if they choose this path, SVWT. So maybe you can try to prove this yourself also at home, but this is what this gives us. Here, we claim that no driver has an incentive to switch here if everyone takes the path S to V to W to T, S to V to W to T, then we claim that no driver has an incentive to switch to some other paths. And this can be this is this very high level argument which I provided that V to T strictly was like is no better than VW to T and everything. So these arguments can be formalized mathematically also, which maybe can be homework exercise for you guys that you should try this yourself. This is not too hard to prove, and that's why I think everyone can do this. So yeah. So we claim that no driver has an incentive to switch to some other path, to any other path. And so basically, uh, what happens is everyone is taking this route, and hence this is Nash equilibria. Hence this is a Nash equilibria. And what's the Nash equilibria? Basically, that everyone is taking the path S to V to W to T. And now, okay. So now we note something very interesting. Like this is a Nash. So here the Nash equilibria was everyone was going through like 0.5 was going through here, 0.5 was going through here. So everyone was taking 1.5 hours to reach from S to T. But here what happens is everyone is taking this path. And so the cost between S to V road is actually equal to 1 because this fraction becomes equal to 1. Similarly, W to T also becomes equal to 1. So now everyone is taking this SVWT path. So everyone is taking 2 hours now. Here, everyone will take 2 hours to reach from S to T. Okay. So what we are trying to say is initially in the initial network, everyone was taking Nash equilibrium 1.5 hours. And why did we install this edge? We installed this edge to kind of reduce the load of traffic goers and say that, okay, like we have installed a very fast edge so that you people can go faster now to from S to T. But now Nash equilibria changes in such a way that actually instead of making the traffic faster, you have made the traffic slower. That everyone now takes 2 hours to reach from S to T. Initially they were taking 1 hour, but now they are taking 2 hours to reach from S to T. And this is something like which you call like which is very cool, and this is something which is called something like a price of anarchy or whatever you can call it. But yeah. So I hope everyone gets what I'm trying to say here. Like, no, An interesting observation is that initially everyone was taking 1.5 hours to reach from S to T. But after trying to, but after installing a road to make the traffic faster, we have actually made the traffic slower. So, like supposedly, what this means is that if in a traffic, if you actually introduce another road, usually what this means is that the traffic should come become faster, right? But now the preferences of people change in such a way sometimes in Nash equilibriums that actually the traffic tends to become slower. So you can't just to control traffic, you can't just say, oh, we'll just install some other roads and now traffic will be like slower or faster. Like traffic will be like faster if you install new roads. It can become actually slower, like here. Even if we are helping the network by installing a road, we have still made the network worse off. This is very counterintuitive. Like this seems very counterintuitive. This seems very counterintuitive. And like this is like a and is called like price of anarchy. Basically, some people like to call this price of anarchy. Something like this. That because everyone has some individual preferences, because of this, even if we are trying to help the network, we still have to pay some cost and like we actually make the network slower. And this we are paying this price of 0.5, and this is called like price of anarchy. And this is also called like uh, this is also called something like this is known as Bayes paradox. Like I don't remember the spelling, but yeah, it's something like this. And this I find like this I think is very cool. Like in spite of trying to help the network, you've actually made the network slower. So yeah. Okay, so I think we are quite much out of time. We have already at Halimi, like the lecture is already of 2 hours. I planned another problem, but maybe like it's again a very similar problem. So I think we can just remove it. But I hope like so first of all, like the problems are very routine problems which were like standard quiz which could be asked in your quizzes or something like that, similar to your quizzes. But the eighth problem was something like which I found like very interesting. Like this is something which involved a bit more thinking from your part, and yeah, I hope everyone goes through this and tries to understand this problem. So yeah, and these are the references from which the problems were taken. So yeah, just mentioning these references also. So, so all right, guys. So I think not a lot of people have not a lot of people have joined the session, but yeah, nonetheless, I hope like okay, so I hope a few of you turn up in like real time also in these sessions. You turn up in person in these sessions also from next time. But yeah, until then, I guess we are done for the day and like hope to see you guys next week actually in person in these sessions. So yeah, till then, like goodbye. Maybe I'll just stop recording and yeah, close the recording. Bye bye, guys, and thanks for listening.